can exist in 7. Aldehydes and ketones can exist in 2 forms, a keto form and an enol form. For example, the aldehyde ethanol exists in equilibrium with its enol form, ethanol, and you're given a nice little picture of it. And you've got your 2 different molecules are also known as tautomers. State which of the tautomers is the most abundant in this equilibrium. Okay, so what you've been given is this number here. This is your K. So that is the ethanol, this one, over ethanol. Ethanol, being clear, sorry. Okay, so we've got so this is our enol form over our keto form. And what we have is 3 times 10 to the minus 7 is our result of this fraction. Now, if you're panicking about this and you're not sure what to do, plug in some real numbers. Make it really easy for yourself. It says, which is more abundant? Well, let's assume that we have 1 over here and 10 over here. It's a nice big number. Okay, so then you would say, okay, so that gives me 10 over 1. So a big number. Let's do it the other way around. What if it was 10 on this side and 1 on this side? 10 on this side and 1 on this side. So our options are 10, 0.1. So this one is the top heavy fraction, gives us a small number. Oh, just realised I've written that the wrong way out. Sorry. That would be 1 over 10. Okay, so what we've got here is our 0.1. So we've got this number here is 3 times 10 to the minus 7. It's got to be this way round. So this one must be the one that is more abundant. So you can say that whichever way you want. So we can say ethanol, or you could say the keto, or you could say left hand side. Okay, you're just putting which one is correct. Okay. For B, 3-methylpentan-2-one is optically active and exists in equilibrium with its enol tautomer. Circle the chiral center on this molecule. Okay, chiral, you have to remember you need a carbon which has 4 different groups round the outside. All 4 of these need to be different, and it has to be 4. Okay, so this one is out because it's got 3 that are the same. This one's out because it's only got 3 things attached to it. This one has 1, 2, 3, 4 different things. That's your chiral center. Okay, this one is out because it's got 3 that's the same, 3 that's the same, 2 that's the same. Okay, so that's your one you've got to circle. Suggest why the optical activity of 3-methylpentan-2-one decreases over time. So you're told it's optically active and exists in equilibrium with its tautomer. If it's optically active, then the other one, the other flip side of it, is going to also be optically active, but probably in the opposite spin. So what you're making, and this is what you want to write to get the mark, this term, racemic mixture. If you get a racemic mixture, then basically for every molecule that's spinning the light one direction, it's being spun the other direction by the other one. So what you're doing is just forming that other optical isomer. Draw the skeletal formula for this compound. I think this is all right. Easiest way I think to do this, we go, that's 1, 2, 3, 4, 5 carbons in a chain. Let's go 1, 2, 3, 1, 2, 3, 4, 5. Okay, and then let's have a look. 1, 2, 3, off number 3 I have a CH3 group. 1, 2, 3, there's my CH3 group, and off number 4 I have a double bond O. That's it. You can, whichever way round you draw it, doesn't matter, as long as you've got the right things there. Okay, you'll see I've just gone and got the mark scheme for this one, because frankly it's going to be a lot neater than my scribbles. Right, possible mechanism for acid catalyzed enolization, I can't even say it, enolization is shown below. We've got the R prime and the R double prime are alkyl groups, and it shows you the mechanism. Using structural formula and curly arrow notation, show a possible mechanism for the acid catalyzed enolization of 3-methylpentan-2-one. Okay, so basically you're just substituting this into that. I first looked at it and went, oh, curly arrow notation, that's going to be a bit of a nightmare, but it's a straight substitution. So if I spin back up a little bit for their original diagram of what this is, that's all you use. So you're just substituting in this and following it through. I don't actually think it's that bad. But I'm assuming that people did awkward things to it. Okay, as I say, look how much cleaner. Okay, so this is just, so what we've got here is the first, here's your initial one, here's your oxygen, here, that's that step. And then we've got these two arrows that we need to bring in, and there they are. Okay, and then we've got our last arrow being the dissociation. So that's basically it. I quite like it. It could be a lot worse. Okay, and they've also given a potentially alternative mechanism that would work as well. I don't know if you would have gone to this, but you could have, which is basically having this CH3 group on the end doing the substitution in, not substitution, the second part of the curly arrow. Okay, this bit here. Entirely up to you which one you went with. I think that one was the one that was clearer. It's okay. And that's the end of the question.